vector space V, we're particularly interested in a set of vectors A that possess the property that any vector little v in set V can be obtained by a linear combination of vectors in A. In this video, we'll have a close look at these vectors and we'll characterize them. Let V be a vector space with the operations of addition and multiplication, and let A be a set of vectors. If every V in V can be expressed as a linear combination of elements from A, then A is called a generating set of V. The set of all linear combinations of vectors in A is called the span of A. If A spans the vector space V, we can write V is equal to span of A. It's a good idea to think of the span of A as a set of all objects that we can make using linear combinations of things in A. Generating sets are sets of vectors that span vector subspaces. That is, every vector can be represented as a linear combination of vectors in that generating set. Now, we want to be a little bit more specific and characterize the smallest generating set that spans a vector subspace. So we'll let V be a vector space and A a subset of V. If A spans V and is the smallest set that spans V, we call A a basis for V. Let V be a vector space and B a non-empty subset of V. Then the following statements are equivalent. B is a basis of V. B is a minimal generating set. B is a maximal linearly independent set of vectors, V. That is, adding any other vector to the set would make it linearly independent. Every vector X in V is a linear combination of vectors from B, and every linear combination is unique. That is, if X is equal to the sum of lambda I bi's, and also equal to the sum of psi I bi's, then necessarily the lambda i's and the psi i's have to be equal for every I. Here's an example. In R3, the standard basis is a set of vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. But that's not the only basis for V. Other bases could be 1, 1, 0, 0, 1, 1, 1, 0, 1, or even something funny like 0.5, 0.8, 0.4, 1.8, 0.3, 0.3, negative 2.2, negative 1.3, and 3.5. Now the set A, consisting of the vectors 1, 2, 3, 4, 2, negative 1, 0, 2, and 1, 1, 0, 4, consists of linearly independent vectors. That is, none of those vectors are linear combinations of the other vectors. But it's not a sufficient set to generate R4. In particular, the vector 1, 0, 0, 0 is not an element, is not something that you can make from elements in A. So, while every vector space V possesses a basis, we can possibly have multiple bases for a vector space. That is, there's no unique basis. However, all basis sets have the same number of elements and the same number of basis vectors. When talking more about generating sets and bases, let's consider only finite dimensional vector spaces for a second. The dimension of V is the number of basis vectors of V. We denote this as dim V. If U is a subset of V, then the dimension of U is less than or equal to the dimension of V, and they're equal if and only if U is equal to V. Intuitively, the dimension of a vector space can be thought of as the number of independent directions in the vector space. The dimension of a vector space, however, is not necessarily the number of elements in the vector. For instance, the vector space V, that's the span of 0, 1, is one-dimensional, even though the basis has two elements. The basis of a subspace can be found if we write the spanning vectors as columns of matrix A. We determine the row echelon form of A, and then the spanning vectors associated with the pivot columns form the basis. Here's an example illustrating how we can find a basis for a subspace. So we have a vector subspace U, a subset of R5, and it's spanned by the four vectors x1, x2, x3, and x4. Now we want to find out which of these form a basis for U. So to find the basis, we're going to solve the sum of lambda I xi equals 0. So we go ahead and write these columns in a matrix form and append our vector of zeros. When we solve this homogeneous system of equations, we see that columns 1, 2, and 4 are only pivot columns. That indicates that columns 1, 2, and 4 are linearly independent, and therefore the basis for U is x1, x2, and x4, or essentially that x3 is redundant and is a linear combination of x1, x2, and x4. The number of linearly independent columns of a matrix A of dimensions m by n equals the number of linearly independent rows and is called the rank of A, and is denoted Rk of A. The rank of a matrix has some important properties. The rank of A is equal to the rank of A transpose. That is, the column rank is equal to the row rank. The columns of an m by n matrix A span a subspace U of Rm, with the dimension of U equal to the rank of A. Later, we'll call this subspace the image or the range. A basis U can be found by applying Gaussian elimination to A to identify the pivot columns. The rows of an m by n matrix A span a subspace W of Rm, with dimension of W equal to the rank of A. A basis of W can be found by applying Gaussian elimination to A transpose. For all n by n matrices A, it holds that A is regular or invertible if and only if the rank of A is equal to n. For all n by n matrices A and an n-dimensional vector B, it holds that the linear equation system AX equals B can be solved if and only if the rank of A equals the rank of the augmented matrix A with B. If A is a real n by n matrix, the subspace of solutions for AX equals 0 possesses dimension n minus the rank of A. Later, we'll call this subspace the kernel or the null space. An m by n real matrix A has full rank if its rank equals the largest possible rank for a matrix of the same dimensions. This means that the rank of a full rank matrix is the lesser of the number of rows and columns. That is, the rank of A is the minimum of m and n. A matrix is said to be rank deficient if it doesn't have full rank. We conclude this section with one final example. Looking at our matrix A, 1, 0, 0, 0, 1, 0, 0, 1, 0, we notice that columns 2 and 3 are identical. So those are not linearly independent, which means that despite the fact that A is of size 3 by 3, its rank is only 2 because it only has 2 linearly independent rows or columns. In our second example, we take the matrix A, 1, negative 2, 3, 2, negative 3, 5, and 1, 1, 0, and reduce it using Gaussian elimination. We get the matrix 1, 0, 0, 2, 1, 0, 1, 3, 0, and this has 2 linearly independent rows or columns, which means that the rank of A is again 2. We'll make more use of linear independence and linear dependence in our later videos.